All right, so we talked about buck converter and boost converter. We realized that buck converter, the power flow is from the higher side voltage, higher voltage side to the lower voltage side. And for the boost converter, the power flow is from the lower voltage side to the higher voltage side. Now, can we have power flow in both directions? If you really look at the topology of buck converter and boost converter, you realize the answer is very easy. If you look at this diagram with the black elements here, it's a buck converter. Power flows from side A to side B, and it's buck converter. So VA should be larger than VB, both of them positive. Now, if you add one diode here and one switch here in parallel, now you will allow the power to flow back through this diode. So when you turn on this switch, the power flows in this inductor, and then when you turn it off, it goes. So from this side, side B to side A is a boost converter. Exactly. So by adding one switch and one diode, and I told you yesterday that even the technology is that the switch and the diode always are together, the transistor and the diode. Thank you. Thank you. So this switch cell is available already in one package, and this is in one package. Even if you want to run this as only as a buck converter, no problem. Or if you want to run it only as a boost converter, no problem. You can use the same switches, and then you just operate it properly. But at the same time, if you want to operate bidirectional power flow, that provides this to you. So I don't have much else to say here, it's clear. Now, we go to now half bridge converter, half bridge and full bridge voltage source converter. So the diagram of the half bridge is this one. So it is the same circuit bidirectional converter that we just discussed. The only modification is that this voltage on the A side is broken down into two half voltages, and from the middle point we take a tap, get a tap, and then this is used as the ground, so to speak. So VA is on this side, VB is on this side. The reason we do this is because in the bidirectional that we just discussed is buck and boost, but still VA and VB, both of them should be positive. So that converter we cannot operate as an inverter. In inverter, we need to change VB to plus minus, so in order to be able to generate AC signal. So with this arrangement, this is the easiest arrangement that you can use to generate a bidirectional voltage. Why? When you turn on this switch S1, this point is connected to this, right? And this point is on this one. So the voltage V is equal to VA over half. When you turn on this switch, now you are connecting in the reverse polarity across this battery. So the voltage here is negative VA over half. So by properly switching S1 and S2, you can generate VA over half, negative VA over half at these terminals. So if this voltage can be positive and negative, this voltage can also be positive and negative. So this is very good to generate AC waveforms, current or voltage. Analysis, let me talk a little bit about analysis. Okay, this is for the previous converter. For the half bridge is here. So now, whenever we move to inverters, for the carrier waveform now, you have to also consider negative and positive. So carrier waveform now is symmetrical. I always consider that between negative 1 and 1 for simplicity, but you don't have to. If you change it with other than negative 1 and 1, you have to bring it into your model. So anyway, so we use this the same PWM, and the output of this PWM now goes to switch 1, which is the upper switch here, and not or complement of that function goes to switch 2, the lower one. So in this case, you make sure that you never turn on both switches at the same time, because otherwise you will short circuit across the two voltages, right? So you don't want to do that. In these type of structures, you never turn on both switches together. That's a requirement. Because if you do that, you short circuit this voltage source, right? Okay, so for that reason, the complement goes to S2. So when M is larger than the carrier waveform, the switch S1 is 1, and when it is smaller than, the switch S1 is 0. I don't need to show S2 because it's just complement of this one. When S1 is 1, now the voltage across, the output voltage is half VA, we said. So the voltage across inductor is half VA minus VB. And then when the switch is off, first switch is off, the second switch is on, the voltage is negative half VA, and the voltage across inductor is negative half VA minus VB. So make sure that this voltage should be positive, this is negative. That's the requirement for this circuit to be stable. Because otherwise, the current will keep going up or keep going down. So the requirement for this circuit to operate is that this should be positive, right? And this should be negative. Okay, so current will go up in this direction, in this region, and go down. In this region, transistor 1 is operating and diode 2. If the current flowing from left side to the right side. If the current flowing from right side to the left side, in this region, diode 1 is working and Q2 for negative current. Okay, so this is the principle of operation. This is the condition I told you. If you combine those two conditions in one equation or one inequality, that is this basically. So it says VB should be between half VA and negative half VA. So the equation for V, the voltage here at these terminals, this voltage here, when this switch is on is half VA, when the switch is off, this is on, is negative half VA. So mathematically, you can say this is this equation. When the switch S1 is on, is half VA. When the switch S2 is on, is negative half VA. So this is mathematical way of representing it. So we can factor out this way. And because S2 is 1 minus S1, so you can say 2S1 minus 1. And then this is the voltage equation. So again, this one and this one fully model this converter, both at the switching level and at the control level. So at the switching level, if you want to show it similar to what we have done before, that's basically what you get. So when switch 1 is on, the current flows this one, and then when switch 2, it goes to this one. Average model, we take the same approach of Fourier series. So the average of V bar becomes VA over 2. Average of S1 is D. Average of S2 is 1 minus D, so it becomes 2D minus 1. Right? And now here is the point. When you use this modulation with these numbers that you have, and this is the point I told you, if you don't choose negative 1 and 1, you have to fix this at this point. When I change M from negative 1 to 1, my duty cycle changes from 0 to 1. So M and D are no longer equal. But this change is linear. So the only equation that can represent this is M equals 2D minus 1. There you go. So you can either use this equation, or if you want to use this equation versus M, you can use this equation. This is better because M is really the input to the PWM. M is the point that you control. Okay, So m into VA over 2, that is V bar minus VB divided by 1 over LS plus R is I bar. So the same mathematical model almost, with the difference here that we have VA over 2, and also another difference that this diagram doesn't show, but in the previous diagrams for the buck and boost, current is always positive. Here this current can be positive or negative, because this voltage can be positive or negative. And as a result, this current can be positive or negative. And this voltage can be positive or negative also, because M is positive or negative. All right. Now that is half bridge. Full bridge is this one. So you have now two legs, one leg here, another leg here. So S1, S2, S3, S4. And then you don't need to break this one into two voltages. Just use this point and this point as the output terminals for the converter. And we are going to claim that this will do the same job and even better than the other converter. Okay. Now, this converter can be operated in two different modes. One is called bidirectional or bipolar mode, bipolar PWM, and another one is unipolar PWM. So let me explain bipolar first, it's easier. Bipolar is when you turn on this switch and this switch together all the time, and this switch and this switch together. That's always you follow this. S1 and S4 together on, and during that time, obviously, S3 and S4 off. And then next step, S3 and S2 and S3 on, and S1 and S4 off. Okay, if you do that, what happens? When you turn this one on and this one on, this point is connected to this terminal, and this point is connected to this terminal. So you have VA here. And then when you turn on this one and this one, this is connected to the lower side now, and this is connected to the upper side. So negative VA. So you can generate VA, negative VA. You see immediately the difference. You can generate twice larger voltage with this one. Other than that, it's basically the same as the other converter. So that's the bipolar PWM operation. I said S1 and S4 are equal all the time. S2 and S3 are also equal, but the complement of S1 and S4. So voltage V is equal to VA into S1 minus VA into S2. And then see the difference is we don't have VA half, we have VA. So 2D minus 1 and M, and that's it. Right? So the only difference is that now we can generate twice larger voltage at the output terminals. Unipolar. Unipolar, the principle is this. Let me see if I have a diagram here now. The principle says, okay, this way of operating the switches is not the only one here. In half bridge, that was the only one. You need to turn on the one and turn off the other one. You have no other option. But here, you have one more option. That option is, if you turn on these two together and turn off these two at the same time. So what you will have, this voltage, this terminal and this terminal, both of them connected to the same point, so the voltage is 0. And the same thing here. So these two new states or new operating modes are called zero states. So in unipolar PWM, we have two zero states, and we can benefit from these two zero states. How we can benefit? When we are sending the current here from this one to this one, from let's say this left side to right side, we only need positive voltage. We don't need negative voltage, positive and 0. So let's switch between positive and 0, positive 0, positive 0, and it's unipolar. It doesn't become negative. And then when the current is coming back, we switch between 0 and negative VA, 0, negative VA, 0, negative VA. So in this case, We can operate the system as both direction, no problem. But the voltage that we generate here is always positive or negative. It doesn't change from all the way extreme positive to extreme negative. Okay. So I will talk about advantages of this. We can talk now. What is the advantages? The advantages for this is obviously when you switch between VA and 0 or 0 and negative VA, this inductor is exposed to a smaller range of AC voltage variations. So the hysteresis loop of the magnetic that is used to generate the inductor, we don't want to go into details of that, right? So now that hysteresis loop is smaller. So the hysteresis losses becomes lower. Immediately one thing. So the hysteresis losses of the inductor becomes lower. You will see in a moment also that for the same amount of switching frequency, let's say 4 kilohertz for this one and 4 kilohertz for the other one, half bridge, this voltage will switch twice faster. So effectively, you can say effectively, the switching frequency of this circuit is twice. When the switching frequency is twice, the switching time is half. So the ripple of the current becomes smaller for the same amount of inductor. Or for the same amount of ripple, you can have a smaller inductor. So that's the second advantage. Any other advantage anybody can think about that? That's these two that come to my mind now. EMI, exactly. Yeah, because again, the switching, the level of the switches is smaller, so the EMI level is smaller. Okay. Yeah, EMI we don't teach in this course, but EMI is also very important for power electronics. Yeah. So EMI lower, inductor lower, and hysteresis loss is lower.
Device rating can be chosen small because now the voltage blocking is going to be half.
Across each switch? No, I don't think so. Is it? It will be the same. I think it's the same. For the same amount of VA, it will be the same. If you use this, yeah, I think you are right, but you just put it this way.
Somehow we are taking midpoint.
Right.
This VA by 20.
Right. No, we can use a voltage VA, half of the voltage that we use there. For the same amount of output voltage, we can use a battery on the VA, which is half of the other one, right? So in that case, yes. Yeah. Right. Okay. So multiple advantages and basically no disadvantage. The only disadvantage is you need to have 2 more switches. Well, now we're comparing with the full bridge, so that's even 4 switches there. So no disadvantage. So only the question is how to operate it.
One disadvantage
Yeah.
there.
Uh-huh.
If I have simulated this,
Uh-huh.
then there is reversal in the current. Suppose you are taking plus command is there, plus current command, and you want to shift from plus to negative.
Mm-hmm.
It will take time to reach from plus to negative.
Mm-hmm.
While if it is bipolar PWM, it
Mm-hmm.
will reach faster.
Mm-hmm.
Because you are switching between.
But again, if you use the same amount of VA, that's true. But if you use half of that VA here, I'm not sure. You have to look into that. But the conclusion is, as far as I know, this is the way to do it. And you can hardly see any people using single-phase inverters that they decide to go with bipolar. They all go with half. The advantage is significantly, if there is any disadvantage, which I'm not sure, but the advantage is there should be some disadvantage. We are in the area of engineering, I agree with you, but let's figure out later. But as far as I know, the advantages significantly outweigh the disadvantages. So almost every application, they use full bridge converter or full bridge inverter, they operate it at unipolar. Okay. How to do that in using PWM? This is the common way of doing it. It may not be the only way, but that's the common. So carrier waveform is compared with the modulation and generates S1 and S2, and negative of that modulation generates S3 and S4. So basically, if you look at this diagram here, you have now M and negative M, and then M is used comparison with this carrier waveform to generate S1, and negative is used to generate S3. So during this time, when S1 and S3 are on, both of them, you have zero state. Okay. So the current, in this case, we have VA and 0, VA and 0. You can also have negative VA and 0, no problem. So the current is going up, down, up, down. And the mathematical model is exactly the same as what we have in the, here I talk about advantages and disadvantages. Doubled effective switching frequency, let me emphasize here. Look at this one, VA. During one cycle of the switching, you have twice number of switches. So that's why I told you it's twice effective switching. And I talked about core losses or hysteresis losses here. And here is the mathematical model, VA into S1 minus VA into S3, and then use the same equation. We derive 2D minus 1, or which is equal to M. And then finally, this is the, I didn't show the diagram because it's the same diagram. Okay, so in terms of mathematical model is the same. In terms of operation, that's the way you operate it in the PWM, just to benefit from this zero state. Okay, now this is the final converter. I'm going to talk about three-phase voltage source converter. The diagram is here. This is the case that we want to use on the AC side, on the B side, want to use a three-phase AC system. So we take the terminals from the midpoint of these three legs, and you have three-phase inductor here, and three-phase AC supply or three-phase load, depending on whether you want to connect it to the power grid or you want to connect it to a load. So modeling of this converter three-phase, there are two ways of modeling this converter mathematically. One way is in the stationary domain, or in the stationary domain, and one way is in synchronous reference frame. And both of them are common. Synchronous reference frame used to be more common. I'm going to explain both of them here, but when we get to chapter 7, in the last day of the class, we will use these models to control the converter. So in the stationary domain, basically, you write down the equation. This is the voltage equation for the first loop here. And this point is called N, Vn. This is the voltage for the second loop. This is the voltage for the third loop. Now, in this course, again, I only use 3 wires. I don't use a ground connection between the left side and the right side. So IA plus IB plus IC is 0 when you have no neutral connection. Also, assume that the voltage Vs has no zero sequence component, so this summation will be 0. These zero sequence components, again, I will talk about that at the beginning of chapter 7 there. So now if you add all these 3 equations together, and then IA plus IB plus IC is 0, VSA plus VSB plus VSC is 0, VA, VB, VC are the voltages that you generate by the converter using the modulation. Assume that you generate them properly such that VA plus VB plus VC is 0. You can do that in your control. If you do that, now add this also becomes 0. So as a result, Vn becomes VA plus VB plus VC over 3, and that becomes 0. So basically what we proved that is under these assumptions, which are reasonable assumptions, this point will have 0 potential. If it has 0 potential, we can remove it from the equations. And then if you remove it from the equations, let's say you remove all these three from the equations, then you will see that this equation is separate from this equation, from this equation. All three equations are separate. So this three-phase system will be equivalent to three separate single-phase systems. One in phase A, one in phase B, one in phase C. And then already we derived the equations for single-phase VSC, half-bridge, by the way. That will be this one. So you have three of these circuits, one for phase A, one for phase B, one for phase C. However, under these assumptions that we made, VA plus VB plus VC equals 0, basically we do not have practically three independent circuits. We only have two independent circuits. So for that reason, it's not necessary to work with three. We can work with two. And that's the concept of a stationary domain or alpha beta domain. So alpha beta domain converts ABC to alpha and beta. And it says, I don't need all three, A and B and C. Let me only derive two, alpha and beta. So there is a mathematics behind that. For every signal A and B and C, this is to define alpha beta. So alpha beta now is a complex signal, you can say, has a real part and has an imaginary part. So for instance, if XA is this one, XB is this one, 120 degrees behind, and X3, XC is this one, which we have in power system, then X alpha beta, which is X alpha plus JX beta, just put these three into this equation as a little exercise, and then you will see that it becomes this plus this. So alpha component becomes cosine, and beta component becomes sine of the same argument. So beta component is 90 degrees behind the alpha component. Okay. Now, if with this equation, it's a linear transformation from alpha beta, so you can apply this transformation to those three equations. And then you convert those three to 2. So these two will be the equations, and then you can show it in one equation. But remember, this has two equations in it, alpha and beta. So this single equation, which has two components, represents the model of the converter in alpha and beta, which is this one. One in alpha, one in beta. So rather than three circuits, we have two circuits. So this is much easier to work with compared to the other one. Okay. However, this is not the most common way of modeling. The other common way, which you may say why we need something even easier than this one, you will see later, is the modeling in rotating synchronous frame. The idea is, if you look at this X alpha beta here, which is this plus this one, and using the Euler equation, that's x e to the j omega t plus delta. What is this? This is a vector which has magnitude x and angle omega t plus theta. So it's rotating. It's a phasor which is rotating. For that reason, it's called a space phasor. So all the signals, AC signals, are rotating. If I can multiply this rotation into negative of that rotation, I can make it synchronous, or stop moving. So mathematically it means if I apply x alpha beta into e to the negative j theta, and theta is omega t. So you cancel that omega t, now suddenly everything stops. So it's physically, what does it mean? It means like you can stay outside the bus and look at the bus, or you can go sit inside the bus. Two ways of analyzing a problem. If you are staying outside the bus is moving. But if you go inside the bus is not moving anymore. Everything else is moving. But you want to control the bus and everything inside the bus. So it's easier if you are inside the bus. You see, so to speak. However, the derivation of equations become a little more complicated because now you need to take derivative of this equation and then go back and derive the equations. Do it when you get home or in your room tonight. And then we derive two equations. You can represent them here as one single equation or two separate equations. And we call them D and Q for these new directions. Both of them are not rotating anymore. So XD and XQ or ID and IQ. So one thing we notice is very similar to alpha beta equations with the difference that this term L omega IQ and this negative L omega ID appear. This comes from the second equation and this comes from the first equation. So these two equations are no longer separate. In alpha beta they were separate. Here they are no longer separate. If you want to show it in a diagram, it will be like this. So you have a coupling between this channel, so to speak, with the first one, and the first channel to the second. There is a coupling between them. Sometimes I use this way of showing. It's a simple way of showing using two arrows rather than this one. And this CM is a matrix, which is this one. So you will see this is the same as this one. Okay. All right. And then if you just ignore CM, make it 0, that becomes alpha beta. If you put CM equal to this one, it becomes DQ. So in one representation, you can analyze and model both alpha beta and DQ. Okay, so converter delays also quickly, we talked a little bit about that. It's very important topic in power electronic converters. We have delays. And these delays come from multiple sources. The important ones are, one of them is digital control delay. We always use digital control nowadays for controlling converters. So we have one sample delay in digital control. And PWM, because of the nature of the PWM, we also have a variable delay, basically. That delay is not constant depending on how the signals are being switched. So there are even books written about analysis of PWM. I don't want to go into detail, but to put it in a very simple term, you can say is a variable delay between 0 to 1 sample, and it changes. So on average, you can say 1.5 delay, sample delay coming from digital control and the PWM. You may have delays in your sensors that again come into the feedback loop, and so on. So we need to make sure that these delays are not, and especially now we are going to operate our converter and we are tempted to operate the converter at very high speed. So we want to make sure that the speed of this converter does not go beyond the delays of the system. Sometimes if you are sure that the speed is really below the delays sufficiently, you don't need to model the delays. But if you want to really speed up your control systems, one way is bring the delay in your control model and use it to design your controller. At some point we will do it in this class, hopefully. So to bring that in your control model, you put a DS here. That DS is this one, e to the negative TD into S. So now you need to work with this transfer function, which is not very straightforward again. So you pay a price. If you want to really speed up and then bring the time constant of your system closer to the delays that your system has, you need to model the delay and bring it in your analysis and in your control design. And then that's the price you need to pay. You need to be able to, from control perspective, work with this system, which is not a very easy system. But we can do, no problem. If you are expert in control, you can do. And like I said, we will do, at least a simplified version is that you approximate that function with this function or this function. These are first order approximations of the delay. And then if you approximate it, it will not be very difficult to work with it. Okay. So let's use those few minutes we have to start the next chapter. Class 3. Oh, we need to open with the other one, sorry. How many of you have not taken at least one course in control? I mean, don't be shy. If it's all right if you tell me. So you have not taken any course in control. Okay, no problem. Because I wanted to know with what speed I can go through this chapter. Say it again. Time varying delays are what? Right. Delay is time variable. It's not constant. Let's put it this way in a inverter application. But we cannot model it as a variable, because if you want to model it in your control design and want to make it as a variable, it becomes extremely difficult, this control problem. And yeah, yeah, right, yeah, yeah. I haven't seen that. If you have that, show it to me. But I would like to see. Yeah, yeah. It's possible. I'm not saying it's not possible, but first of all, I believe it becomes very complicated. Second, you need to prove we need it to do that, and we achieve something. If you solve something and then you cannot prove that you achieved something, it's not, people do not accept from you. So the common practice is either consider 1.5 sample delay or extreme 2 sample delay. Or even occasionally I have seen people considering more than 2 sample, because they say, okay, let's say I have also some delay coming from my sensors and everything, I have 3 samples delay. Yeah, the worst case scenario. And then design your controller for this 3 sample delay. I don't know which one is better. But anyway, for your particular application, you need to figure out. If I want to again summarize, if you are not, the responses of your control system are not approaching the delay, amount of delay that you have, you don't need to worry. But if you really want to make it faster and faster, and you realize that the time constants are become closer to the delays, then you have to model it. One scenario, one case that this happens and we do not have much control over it is when we use LCL filters. I don't know if you are familiar, LCL filters. And if you want to do active damping of LCL filters, you need to increase the speed of the controller. You cannot make it slow. Now, when you increase the speed becomes comparable to the delay. Then you have to include the delay in your control model. So people who design controllers for LCL filters, they know how to do it. They consider delay. And we do also one example, hopefully tomorrow or the day after tomorrow. Yeah. Okay. So the way I proceed is I have 2 chapters here in control. To this class and the next class will be completely control, no power electronics. So for the moment, for these 2 classes, no power electronics, only control. And I'm teaching controls, the basics of the control. And then after these 2 chapters are done, we come back. Now we learned how control works, and then we come back to power electronic converters. We have already known how to develop the control model. So we have the control model of the converter. We know how to design controller. Let's do together, combine them together. So the first section here, first chapter, will be frequency domain approach. frequency domain or transfer function approach is the classic control approach. And the other one is state space, which is more recent, I would say. So in the frequency domain approach, it's based on Laplace transform and transfer functions. But let's, before going to details, at least define a few terms, because these terms we use all the time in control. It could be, say, a system or a plant or a process. It's a system that you want to control. If it's a converter, that converter, we call it a plant or a system or a process. These are the terminologies that people use. Output. Output is the particular variable in that system that you are interested in. If it's a converter connected to the grid, you want to control the power or current, that's the variable. If it's connected to a load, you want to control the voltage across the load, that's the variable. If it's connected to a PV panel, you want to control the voltage across the PV panel, that's the output. So output is the variable that you want to control. Input. Input is the variable that you use to control. So in all the models that we derived for the controllers is M, modulation index, right? So by changing M, we can control. There is also another thing called set point. That's sometimes people confuse set point with the input, because in diagrams, set point is like an input to the system, but we don't call it input anymore. In control domain, we call it set point or reference or desired output. We don't call it input. So let's say you want to control the voltage of this converter to be 400 volts. This 400 volt is your set point. It's not the input. The input is the modulation index. Okay. So transfer functions and Laplace transform. Laplace transform you probably know, but if you don't know, I briefly passed through here. Maybe I should have spent a little bit more time, but just in a footnote. So that's the definition of a Laplace transform. If for any function f of t, you can convert it to f of s, capital F, by taking this integral from 0 to infinity, f of t in e to the negative st. This is probably the most important transformation that you can see in engineering. Yeah, it really has much applications in every area. And then Fourier transform can be derived from this one, Z transform from this one, really if you look into that. So this is the mother of all the other transformations, Laplace transform. If you haven't been exposed to Laplace transform, just pick any standard control book, and then there will be a few pages talking about that. You can read and then find out what are the properties of Laplace transform. It's a linear transform, has linearity problems. And the main important property that this transformation has is that it can convert a differential equation into an algebraic equation. That's basically the key. So if you have a linear time invariant differential equation and apply this transformation to that differential equation, now all differentiations will go away. And we know working with differentiations are difficult, has been very difficult. So this will remove that problem. So now for any system that has a differential equation, if you apply Laplace transform to that system, you will derive a function like g of s, which is ratio of ys over us, and that will be a function of s. So any linear time invariant system, you can represent it as this model. And this is the transfer function model of a linear time invariant system. So you can either use, remember, you can either use block diagrams, differential equations, Laplace transform, just to model one physical system. These are different ways of modeling a physical system. This is one model of the physical system. We already used it in converter, like 1 over Ls plus R. Okay. In MATLAB, you can use TF, the command TF, and then give these coefficients, and it actually generates your system. So this transfer function and this differential equation are equivalent. Now, transfer function for linear time invariant systems that we work with is always in this form. It has a polynomial in the numerator, a polynomial in the denominator, and the order of this system is this n, the power of s in the denominator. The roots of this polynomial in the denominator are called the poles of this system, and you will see in a moment why. And the roots of the numerator are called zeros of this system. Only a matter of definition. And poles and zeros, again, MATLAB can generate. I mean, as far as transfer function, MATLAB can do everything. And it's very powerful, and we use a lot of them these few days. And now, if you have a transfer function, you can also take Laplace transform inverse, your inverse Laplace transform. So if you have a function like this, according to partial fraction expansion, you can write it this way. Which P1, P2, all the way to Pn are the poles of this system, and R1, R2 to Rn are called residues of this system. And now take Laplace transform inverse. Each one of them, this gives you an exponential function. And here basically tells you why we call them poles. Because the response of this system, this Laplace transform of the transfer function, basically shows the natural response of this system in the time domain, has n components. And each component is called a mode, by the way. Mode. In control, when they say modes of a system, e to the p1t, e to the p2t, these are modes. Every response of this system is a combination of these. So these P1, P2 to Pn shape the response of this system. These are the most important parameters of this system. These are poles of this system. And another thing we can see is that if P1, P2, Pn are on the left side of complex plane, because these are, generally speaking, complex numbers. On the left side of complex plane, this goes to 0. But if any of them is on the right side of complex plane, this goes to infinity. So that is what we use the term stability. If a system, the response of this system can remain bounded, we say this system is stable. If they grow and go to infinity, we say this system is unstable. So immediately you see the condition. We can mathematically prove all the details, but it's not necessary. So the condition is all the poles must be on the left side of complex plane. If they have that condition, the outputs of this system remain bounded for every bounded input. So as long as the input is bounded, the output is also bounded. This is a stability. MATLAB can generate the step response. Impulse response we don't really need. And this LSIM generates the response to any input that you apply. Stability, I already talked about that. Now, disturbance and uncertainty, very important things. In every practical control system, we have two things, disturbance and uncertainty. Already in the converter, what we said, VA and VB, we may not know exactly what they are, or R is, that is uncertainty. There is another thing that can happen, which is disturbance. Disturbance is a force that comes from outside to the control system, and you do not know exactly when and how much happens. Right? That's the definition. Or there is at least one factor of stochastic nature in that disturbance. That is called disturbance. If you know exactly what time it comes and how much it is, we don't call it disturbance anymore. Right? So at least there is one aspect to this signal that you don't know how much is that. Right? And if you really look at every control system, you can find out a disturbance. It's there. Even in the converter, with VA and VB, if you assume VA is 100 volt and turns out to be 98, we don't call it this disturbance. But if it is 100 volt and at some point suddenly jumps to 98, we call this disturbance. Okay? So this is a fine difference between disturbance and uncertainty. Uncertainty, okay, I will explain that later. Now, okay, let me explain and then I'll come back to. Uncertainty is when you don't know one parameter that you have in the model, mathematical model of this system, some parameter you may not exactly know. You assume VA equal 100 volts, but you are not 100% sure that is exactly this amount. This we call it uncertainty. Right? Okay. Another aspect, uncertainty is a very diverse. Another aspect of uncertainty is that, which is important in converters also, is if there is a component in the physical system that our model does not represent. So there is a difference. You may represent it, but you may not know exactly how much it is. That's one aspect. Or you may not even represent it. Just completely forget about it. For instance, that variable nature of the PWM delay. We did not consider that in our... So that's uncertainty, but it's unmodeled uncertainty. Right? Yeah, but resistor of the inductor, we model it, but we don't know exactly how much it is. That is a modeled uncertainty or parametric uncertainty. So uncertainty basically is. As far as disturbance, there are three ways of modeling a disturbance. Disturbance either comes to the input of the system or to the output of the system or somewhere between input and the output. Okay, I will tell this one and close this class. Statement of the control. Now we are ready to say what do we mean, what do we want by control. In control, we have some set point and we have some output. We want our output to be equal to this set point. We want the converter to deliver 10 kilowatt. That's what we want. That's the control problem. But what is the problem? There are disturbances and uncertainties. So the statement of the problem is, let me see if I find the control input, U, which in our case is the modulation signal, such that the actual output of the system, Y, remains close to the desired value. And this despite the disturbances and despite the uncertainties. So it should reject the disturbances and it should perform robustly against the uncertainties. So that's the statement of the control problem. Let's see. I think I can give this after in the next class. Is it good time to stop or should I continue?